Okay, we are having only 52 participants. There are nearly 180 participants, but it's fine. They will be joining. Keep on joining. So, shall we start, sir?
Yes, 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 please.
Okay. So, good afternoon, everyone. I welcome all of you to this last session of third day FDP program on recycling of plastics for sustainable growth. We are having with us Dr. Pradip Kumar Maji. He is currently working as associate professor at IIT Roorkee, and he has completed his PhD from IIT Kharagpur. Before going to PhD, he has done his BTech and Masters from Calcutta University in Polymer Science and Technology. Then after completing his PhD, he worked as a scientist for 4.5 years in DRDO before joining to IIT Roorkee. So he joined as an assistant professor in IIT Roorkee, and then he is continuing working over there. He has more than 90 publications in several reputed journals and published many book chapters. His key research area is on polymer nanocomposites, graphene-based composites, then rubber technology, then several applications of polymer composites, and so on. So now I request Professor Maji today for today's session. His talk is titled as Value Proportionate of Bio Waste. So he will be addressing our participants. And sir, I am requesting you to address our participants. And for this faculty development program, our participants are mostly the faculty members, assistant professors, and from various polytechnic as well as AICTE approved technical institutions. So I request you, sir, kindly address them.
Thank you very much, madam, for your kind introduction. So I'm really thankful. I'm thankful to Dr. Mohapatra, who has invited me to give this speech. And
yes.
Dr. Mohapatra is Dean and Coordinator of ATAL FDP, CIPET Bhubaneswar. And I'm thankful to Dr. Giri, who is also working as Assistant Professor in CIPET, who has introduced me to Dr. Mohapatra. And today, are you able to see my screen?
Yes, sir. Yes, sir. Your screen is visible.
And I make it full screen. Okay. Is it okay?
Yes, sir. It is visible, sir.
And today is one of the memorable day for our society. Today is the birthday of Swami Vivekananda.
Yes.
This is basically always we used to think we are youth, and he is the basically icon for us, those who are till think we are youth.
Yes.
Just I'm coming to the basically topic. The topic of the whole theme is that recycling of plastic for sustainable growth, and my specific talk is value proportionate of bio waste, sustainable advancement of nanocellulose-based polymeric material from lignocellulosic bio waste. So before going to that particular topic, whatever I'll be talking in details and some research aspect, whatever I have done with the bio waste material. So I'll start in different way. If you see, just whenever we are talking about the recycling of polymer wastes for sustainable growth, generally we used to see most of the time it is downcycling. Downcycling means like one plastic bucket, whatever you are using, so after some certain point of time, when it is broken or something else, then we used to do the remolding of this particular material, and we are utilizing for some other application. And if you see that its value addition is decreasing, basically rather just we are downcycling. Downcycling means property of this material is decreasing. Property of this material is decreasing. Okay, there are some other aspect that upcycling. Actually, if you see, if we are able to do the upcycling, that will be more sustainable. That one plastic waste, whatever we are using, if the waste is giving more value addition to the system, then that is always useful to us. And today, researchers are trying to do some research with that of the upcycling of the material, upcycling of the polymer. Okay, but here I will be discussing the upcycling process, or basically that whatever it is waste, that if we able to use this waste, and definitely as my topic here, it is not the exact polymer, rather it is bio waste, that rather I can call it the biopolymer waste. That biopolymer waste can be utilized for the sustainable application, or I may tell it as a basically upcycling of the material. Where there is no value, then I am trying to get the highest value from this material to utilize for the some other application. Let's start this particular topic, whatever I am interested to speak with you. This is basically, if I start this lecture in that way, can you please imagine that a representative from IBM and Bell Helicopter Textron would be keynote speaker at a pulp and paper industry conference, and they would be asking the industry for a new innovative bio-based material to use in their mainline product. Mostly then any helicopter or any aerospace industry or any basically high-end application material, basically carbon fiber we used to use as an advancement for the implements composite material. But we can think that paper and pulp, basically it is nothing but the cellulose. If we are able to use this cellulose for the mainline product as a reinforcement, and definitely my interest is that this cellulose I want to extract from the waste. And that's why here just I am a speaker to introduce that type of waste that can be utilized for the advanced application. Let come to the one cartoonistic demonstration way that why I have taken this cellulose as my material to the application of in the different aspect. This is the two trees that are standing to each other. So one is thinking just to become old. Okay, but another is telling you, see, we are old, but we are very strong enough. Okay, because today day is basically nano. Everywhere if you ask, it's a nano car, nano particle, nano composite, your chips, whatever you are using, that is the nano material people using, MEMS, whatever people are using, that is also nano material. So everywhere it is nano. They are thinking, yes, definitely something is there with us that is nano material. That's why we are very strong. What is the nanomaterial? What is the nanomaterial? Basically, if you see, cellulose is the nanomaterial here, that is the building block of the tree. And here, if you see this tiny nanocellulose material, it has the property that can stand for the basically build a very good mechanical property to stand still for the long duration of time. Here, I must have to tell it is not only the cellulose tiny nanoparticle, but also some other material like as a matrix, it's a lignin and other hollow cellulose, hemicellulose, that's it's make a composite material in the wood. That's why this wood is very strong and tough, and it can sustain for the long duration of time. So light, and as it is there, that the nanocellulose I am talking about, it is very, very lightweight, strong and stiff. Okay, let's more opportunities counting. Mr. Tree, then I used to give food to the people, to the animals. I used to give the shelter. I used to give energy also. Okay, so I'm feeling bored, and Newton must be grateful to me that without my presence, the Newton cannot be develop that gravitational force. He must be happy for my presence. Okay, but most of the times, whatever I am talking about, this is the first generation of use of my material, that is the shelter, food, everything. Now, if I am coming to the little bit in the next direction of this uses of this material, then that is the basically tree we are utilizing for making the furniture, for making the basically different type of showpiece, all the things we used to use. But during processing, there is a lot of waste. Not in spite with that of things, the waste, whatever I'm talking about for the wood, if I take it to the basically paddy or your wheat, that is the waste of the paddy and wheat, whatever we are utilizing, that is the wheat straw and the rice straw, that is a major concern nowadays. In North India, basically, we are surrounded by your Delhi, Punjab, Haryana, and West UP, there are a lot of paddy field and a lot of basically waste, your wheat straw and rice straw. What agricultural people used to do it? They used to burn it, okay, to clear it. Now, if we able to utilize that waste material, that is the agricultural waste, to the mainline product, that definitely it will be upcycling. And I am here to discuss that type of thing. If whatever I am utilizing, whatever I am getting the waste material from the furniture industry as well as the agricultural field, if I able to make this product or waste product to a value addition, to a basically high-end application, then this is must be a basically one type of upcycling process. Various type of wood waste, sawdust, cut up, trim, brick, and I have told you also waste from the agricultural field. This is basically most of the times you will be seeing left without any concern, dispose of landfill. And you may tell me then there is no requirement to do the recycling because it is bio waste. It will be degrade over a period of time. That is true. I'm not denying that thing. But thing is that if we able to recycling that particular polymeric material that is already there, though it is a biopolymer material, cellulose, and if we able to extract that material, why not? Definitely we can give the some other value addition process with that of the material. Okay, just I am here. I will be discussing that part. Okay, so that's why rethink is required with that of the tree. This I am benefited. I can be explored in different way. Think the tree that it can be utilized for the some advanced application like your fiber in the car application, in the bulletproof jacket, in the water filtration application. There are a lot many way we can think. But so let's target to explore the secret behind it. The secret behind is that basically this is the cellulose. So if we know the cellulose in better way, then definitely how this cellulose can be utilized for the advanced application, that can be conclude that high-end application, how I can utilize, how I can tailor, or how I can modify it, or how I can mix with the other material to make a composite for getting a good value addition of the final product as well. You see, this is the basically a beta D glycosidic linkage is there in the cellulose, and that is the basically called cellulose unit. Cellulose unit is very important here. This is the difference between your cellulose to the starch. Here, basically, beta glycosidic linkage is there, but in the starch, this is the alpha glycosidic linkage is there. If it is alpha glycosidic linkage, this is water soluble, but as it is a beta glycosidic linkage, it is water insoluble, and that helps us to utilize the material as a reinforcing material. Okay, and this cellulose material, you must have seen that whatever we are using the cotton fabric, all the things, that is nothing but the cellulose. Basic material is cellulose, and definitely some modification we have done for our user actual application. But main constituent, whatever you are using, that is a beta glycosidic linkage, and that is helping to make its stability in the normal environment as well. Okay, this is the basically cellulose unit. Okay, there are different type of source. It's maybe the your wood, it's maybe the sisal fiber, it is the hemp fiber, it's maybe the algae, it's maybe the bacteria, it's maybe any lignocellulosic waste or any lignocellulosic mass that has the main component of your basically cellulose. That's why from the nomenclature itself, you will be seeing lignocellulosic. That is the lignin is there and cellulose is there. Here, just I'm not concerning today for my lecture. That is the lignin part, or otherwise I can get the lignin as well, and I can just extract the cellulose as well. And I am concentrating here only with the cellulose. And if I get chance later on, then I can give you the in details how to extract the lignin as well as the cellulose also. Okay, the hierarchical structure of the wood, if you see, but wood, it's maybe some few meter of height, and transfer section of the wood is few centimeter, and cellular structure, it is somewhere few micrometer. Cell wall structure, again 25 to 30 micrometer, that has inner layer, middle layer, outer layer, primary wall, middle layer, all the things it is middle lamina, but so a lot many things is there. And if you see that is the integrated lignin, cellulose fiber inside is there, and hemicellulose surface cellulose fiber it is there. That's why it is very, very strong. This wood is nothing but the composite of your different type of lignin, different type of cellulose fiber. It's maybe the hemicellulose, it's maybe the hollow cellulose, or it's maybe the cellulose fiber, it's maybe the cellulose crystal. Okay, now if we are able to do the fabricate this cellulose fiber, if we are able to extract the cellulose out of this cellulose composite, then we will be getting cellulose fiber or cellulose crystal. In cellulose, there are two things. There is one is order structure, and another is the amorphous structure. From the amorphous structure, we used to get the basically cellulose fiber, and from the order structure, we used to get the cellulose crystal structure and cellulose crystal. I'll be discussing just now itself. Just now itself, what is the property of cellulose material, cellulose chain. What I told you, there is the amorphous part as well as this is the basically amorphous part, and this is the basically crystalline part. This crystalline part is important and useful for us for making the basically cellulose nanocrystal, and from the amorphous part we used to get the cellulose nanofiber, and definitely from the cellulose nanocrystal, mechanical property will be very, very high. Cellulose fiber mechanical property will be little less. Let's come to the basically some property. Cellulose generally defined as material with a diameter. Nanocellulose is defined as the material which has the diameter below 100 nanometer. Essentially, a wood fiber broken to a nanoscale level. And classification of nanocellulose based on preparation, source, and method of and its dimension. That is called microfibrillated cellulose. That is MFC or cellulose nanofiber or nanofibrillated cellulose. Nanocrystalline cellulose, that is NCC. Of what I told you, there are two parts here. One is crystal, another is amorphous. From the amorphous part, it is a microfibrillated cellulose, and from the crystalline part, we can get the cellulose nanocrystal. And another new type of cellulose is there that is generated by the bacteria only. That is called the bacterial nanocellulose. If you see the bacterial nanocellulose is very much basically for the biomedical application, and purity of the bacterial nanocellulose is very, very high, because fabricated cellulose, CNC and CNAP, whatever we are using, we are getting from the basically some lignocellulosic material. That's why some purity will be an issue. But for bacterial nanocellulose, as it is bacteria used to generate the cellulose material, and that's why this purity of the cellulose is basically very high. Many favor of the nanocellulose, whatever I told you, cellulose nanocrystal, length is 100 to 250 nanometer, and basically diameter is 5 to 70 nanometer. And if it is cellulose nanofiber, then it is length is 7 micrometer and diameter is 5 to 100 nanometer. And cellulose nanocrystal, it is nothing like the rod-like structure. Basically, it is, we call it rice structure. And for the cellulose nanofiber, it is fibril structure, and it has basically one type of Maggi type structure or spaghetti type structure you will be getting. And bacterial cellulose, basically what I told you, this is the like a cellulose structure what we used to get with the bacterial cellulose, but purity is very, very high with the bacterial nanocellulose. Okay, now I am trying to extract the cellulose nanofiber from the any lignocellulosic waste. It's maybe the wood waste. It's maybe the basically your non-wood waste. It's maybe the your basically softwood or hardwood. Anything I can take it and I can get the basically extraction. But let's start with that of the how people have come up with that of the cellulose can be extracted from the any lignocellulosic waste or lignocellulosic mass. First hydrolysis of the cellulose has been done in 1949, and they used to use the HCl and sulfuric acid as a basically extracting agent. And 1983, first preparation of cellulose nanofiber. Basically, they used to use the basically homogenizer as a basically for making the microfibrillated cellulose. Okay, 1992, helicoidal self-ordering of the cellulose microfibrillary in aqueous suspensions was reported. Then 1995, first application of nano-reinforced filler in composite in styrene and butyl acrylate copolymer latex. People have reported that thing. First application of cellulose nanofiber in the polymer matrix. And 2011, first pilot plan for production of nanocellulose by the research company Innovencia in Stockholm, Sweden. And Sweden, they are the basically pioneer for utilizing the cellulose material and basically for the nanocellulose material. If you see, cellulose is very old, but utilization of this nanocellulose, it is not too much old, and that's why over a period of time, as there is a requirement of the biomaterial to utilize in the mainstream application. That's why the reinventing the wheel of cellulose as a nanoform that is come into the system. 2015, according to the statistics, MRC, the global market cellulose nanoparticle reached almost 66.8 million pound, and that's what I told you. What have I started the 2012 international conference that people have introduced, and today in the IBM and the helicopter Textron Bell helicopter, they are utilizing some part inside the aircraft that is used, that is with that of the cellulose nanocrystal material to reinforce their basically structure inside the aircraft. But what I want to conclude, yes, there is a really scope till now to utilize the cellulose nanomaterial for the different advanced application. 2021, the global market of cellulose nanoparticle projected is very high, $808.29 million. Okay, according to the MRC statistics. Okay, and it is keep on increasing. It is keep on increasing the demand, and we have to think how we can basically how we can basically meet the demand to the basically society. There are different nanocellulose research that is going on in the worldwide industry, academia, government, and as well as in India also, we are not far behind. And there are few groups, those who are working like myself and IIT Kharagpur, IIT Mumbai, then IIT Kanpur, people are working with the cellulose nanofiber, extraction of cellulose nanofiber, scale-up technology. And in India, ICAR Sirkat, Mumbai, nanocellulose plant, they have basically set up and a unique facility in line with the Make in India effort by the government of India, was inaugurated by Padma Vibhushan Dr. R.A. Maselkar to produce the nanocellulose. Till date, they are struggling to increase the scale up of the product because deep fabrication of the cellulose, it's a really difficult process. They are trying to do and they are trying to scale up the basically manufacturing process. So there are different type of application of the cellulose fiber, cellulose nanofiber. I was in Japan for a few months, 6-7 months, and I have seen, and I was associated with the Kyoto University with the Toyota Motor Company, that they are trying to target. They are trying to develop the material which can be replace the basically your carbon-based material or organic polymeric material by use of your normal cellulose material. Almost some 70% of the polymeric product that has been replaced with that of the cellulose nanofiber, cellulose material, or derivative of the cellulose. Okay, that's why that it's a large potential of the reduction of the carbon dioxide. Its weight can be reduced. The weight can be reduced, and just I am fortunate. I have till date I'm working with the Kyoto University to develop particular parts where thermal insulation will be giving of this particular material, of this particular product. And here only thing is that your engine part and tire on some metallic parts, almost everywhere we are using the cellulose, other cellulose derivative. And Tokyo 2020, they showcase their product. They showcase their product with another basically cellulose-based carbon vehicle that is called the nanocellulose vehicle project. Nanocellulose vehicle project, and it is really successful, and it has already been launched. This is the basically showcase. I have visited that particular place. Okay. My question is that why nanocellulose? Why nanocellulose? The material from the forest will save the world. Okay, nanocellulose has basically, there are several advantages. That's why we are very interested with the nanocellulose. Number one is high strength. Really, as a fiber of nanocellulose, it's very strength is high. Finer wave-like structure that will help to do the basically making a fiber out of it to utilize for the different advanced application. High crystallinity is there. If you want to utilize this crystallinity of this material, then yes, cellulose crystal is there. Density is very low. Thixotropic behavior, it's a rheology modifier we used to use. Thixotropic behavior. Cellulose gel we used to call cellulose hydrogel, because there are a lot of weight group. This weight group is very important for us so that it can make a thixotropic behavior. high reactivity. Again, due to the presence of OH, that reactivity is very, very high. And anything you can do the modification, based on the modification, you can utilize your material in the different advanced application. High surface area, as I'm talking about the basically it's a nanomaterial, then surface area is very, very high. It is biocompatible because source is very, very, it's a bioorigin. That's why it's biocompatible, non-toxic. Most important thing is it's abundantly available and biodegradable, which will not create any problem to the environment. Rather, it will reduce the environment load by reducing the emission of carbon dioxide, as it is generally basically biodegradable, and that's why it is very easy to use, or basically it is safe to use in the basically system. But thing is that somebody one day asks the question that if it is biodegradable, then how you can utilize for the advanced application? You see, it is biodegradable in a certain environment. It is not degradable if you put it in the normal dried condition. It is biodegradable in the basically microbial condition, as well as in presence of oxygen or in presence of moisture. Without the moisture, it will not degrade. Then if you are able to make a dried environment, then definitely your material will not degrade. And that is the beauty of the material, so that as when required, you just throw it away to the environment, where dumping weather is there, then it will degrade automatically. So I'm comparing the nanocellulose with the competitive material, nanocellulose or nanocrystal. If you see, mechanical property, tensile strength is 7.5 GPa. Okay, modulus is 145 GPa. But as compared to the glass fiber, aluminum wire, steel, graphite whisker, carbon nanotube, you will be seeing our material is very good than the glass fiber, aluminum fiber, or steel. Steel specific strength is very less, but cellulose nanocrystal specific strength is very, very high. But carbon nanotube material, its mechanical property is very high than the cellulose nanocrystal. I'll be comparing the cellulose nanocrystal or cellulose nanofiber to carbon nanotube. And if I show you that basically this relative comparison to the other material, that nanocrystal density, it is very, very less. It is 1.5, and that's why specific gravity of the material will be very, very less. As a result of its specific tensile strength, specific strength of the material will be very, very high. So if I compare to the cellulose nanomaterial with carbon nanotubes, whatever I have shown you, the carbon nanotube is much more higher mechanical property in terms of its modulus as well as the tensile strength. That definitely there are some advantages of cellulose nanofiber. So what is that? If I compare the physical property first, if you see length, diameter, CNC, it is in the nanometer range. And if you see that it is really less than nanometer also, single one nanotube or carbon multiple nanotube. Here, as the nano dimension is getting reduced, the surface area getting increasing, and mechanical property with that of the other material will increase manifold. Length, definitely micrometer, here several micron. Size distribution, polydisperse. Tensile strength, definitely we are a little less than that of the comparison of the carbon nanotube. Carbon nanotube, if you see, it is 13 to 52 GPa gigapascal, whereas we are getting only 2 to 6 gigapascal. Young modulus, again, it is 50 to 143. Here, if you see, 0.32 but 1.47 terapascal, it is huge. Conductivity is there. Here, conductivity is not there. Optical property is transparent, but it is not transparent. That whatever I am trying to show you here, basically, if I compare now, the carbon nanotube property is very, very high. But if I go to the other aspect, manufacturing cost, try to compare the manufacturing cost. Carbon nanotube or multi-wall carbon tube, single-wall carbon nanotube manufacturing cost, energy requirement you see, means how much? 27800 or 250 means a kilowatt per hour. You see, it's very huge, whereas the energy requirement of manufacturing of the cellulose nanofiber is very, very less. Means making cellulose nanofiber is energetically feasible. Source is very easy. It is cotton, it is hemp, it is wheat, anything we can utilize. Where cellulose nanofiber, lignocellulose mass we can utilize. Here you have to use a fossil fuel. Major application, there are different measures, but cost, try to see the cost. It is one basically pound per gram, And here you see almost 15 pound per gram, $15 per gram. This is very huge. There is a huge difference. Notwithstanding the cost and mechanical, but all the details, main concern is that ecotoxicity and disposal. Ecotoxicity of this material, cellulose nanofiber material, is very, very less. Otherwise, if I tell it, it is not toxic at all. Whereas, if you see manufacturing of cellulose, means a carbon nanotube, it will be very environment not feasible, as well as it is basically oxidation stress or flammability, inhalation, or it will damage if you basically inhale during the manufacturing process, because its dimension is very, very less. It will create a problem, and it is not degradable at all. So that your energy, price, and application point of view, where high-end application is required, definitely carbon nanotube you have to utilize. But where that type of mechanical property is not required, here you can definitely utilize the cellulose nanomaterial for the reinforcement material. Okay, this is the basically reason just I'm interested in the cellulose nanofiber. Cellulose nanofiber, there are different type of utilization of cellulose nanofiber as a reinforcing agent. Then you can utilize. And not only that, you can utilize in the biomedical application also, because it is biocompatible and there is no cytotoxicity of this material. Nano paper for the packaging application, already we have developed that nano paper that can be utilized for the different application. Packaging application, it will be little bit costly nowadays because extraction process is little bit costly. But otherwise, if you see environmental point of view, this nano paper is very good. Very good. It is not creating any environmental hazard, number one, and it is transparent also. That's why we are thinking, why not utilize this nano paper for the high-end application like your screen display system or all the other applications where high-end cost is not be issue, but other property can be will be issue. Flexible substrate we have already developed. I'll be discussing that thing. Then it can be utilized for the thermal jacket. It can be utilized for the thermal insulation property. And whatever we have developed, it is very, very lightweight. It is super hydrophobic. We have modified, and it is super thermal insulation also. We have developed in that way. Definitely, it is not the cellulose nanofiber, and we have to add some other material to get a good desired property so that we can utilize for the targeted application. So there are various production methods. For the cellulose nanofiber, cellulose nanocrystal manufacturing. This is the mechanical method. Another is chemical method. People used to do the mechanical homogenizer, the microfluidizer, ultrasonication, refining, grinding, cryocrushing. People used to use. And some people, they have already reported that chemical method, that is the alkali treatment and acid treatment. Here, everywhere, if you see, the energy consumption is very, very high. I'm not comparing with the cellulose carbon nanotube, but still, if I compare the process, still what is requirement is very, very high. That's why I'm trying to develop a particular product processing of this particular product, so that energy requirement will be little less, number one. Number two, it can be little better of the green process. So this is our scheme, whatever we have developed, and we have published also. It has highly cited, one of the highly cited paper, just we have developed that from the raw mango fiber, raw wood mango fiber we have taken. Then we have done the dewaxing. We are soaking in the DMSO. Then we have used the acidified sodium chloride. You see, we have used the acidified sodium chloride that is used as a basically removing of the lignin. Later on, we used to use, you see, 4% QH, very minimum Q, a percentage of acid and alkali we are using to basically remove the hollow cellulose inside the material. After the removing of the hollow cellulose, we used to go for the ultrasonication. So with the minor ultrasonication, we used to get the transparent material. If with the transparent material and the basically bottom material, again we used to dilute it and recentrifuge it, and again we used to get the transparent material. We used to go for the freeze drying method. In the freeze drying method, we can get the basically fine carbon cellulose nanofiber material that for the further application of this particular material. This is the mechanism. Succinate after succinate. that acidified sodium chloride, that is called the delignification process. During the delignification process, lignin will be removed from the system. Only thing is that cellulose and hemicellulose and surface cellulose fiber will be there. This is the reactions mechanism, and this is the different type of lignin that is present in the wood and non-wood fiber. Okay, and that is to give the superior part strength, but you have to remove this lignin. And finally, this is the basically total schematic diagram that you used to use for getting the basically cellulose nanofiber. This cellulose nanofiber, whatever we are getting after the removal of lignin and alkali treatment, that the hemicellulose that will be removed, and only thing is that cellulose part will be there. The cellulose will be basically ultrasonicated to get a microcrystalline domain and amorphous domain material. As a result of it, we will be getting cellulose nanofiber. And if we want to get the cellulose nanocrystal, we have to go for the basically acid hydrolysis followed by basically your basically some osmosis process. This thing have separation process, so that we will be getting the cellulose nanocrystal from this particular material. Okay, this is the basically mechanism what I told you, that we have calculated the yield from the cellulose nanofiber. Means till date, that yield cellulose nanofiber obtained after mechanical treatments 40.97%. Yield is 1 minus weight by other. This is the basically equation. Yield of cellulose nanofiber, it's 31.13%. Reprocessing is increasing up to 73.05%. It is almost, or it is a little better than that of the already reported value by Mestra et al. And Cherian et al. In carbonated polymer. They have reported 69% and 71% yield. So if I compare, we are reaching up to the 73% of the cellulose extraction cellulose material. Pure cellulose material, definitely, just we have checked with the purity, we have checked with the purity of the material, and we have checked with the raw material and extracted cellulose nanofiber by ASTM method. We have seen almost 94% of purity we are getting, 94% purity of the cellulose we are getting, but the estimation by ASTM method. But notwithstanding that, we have checked with the FTR analysis also, whether removing of the other material like your lignin, all the things, whether it is removed or not. If you see 1738, that is the response to the carbonyl peak of the lignin, that is totally removed in the system. And the blue and the red color, that is the cellulose fiber after chemical treatment and cellulose nanofiber. Then there is no lignin peak, means it is totally removed the lignin. And as a result of it, what happened, though I have told you it is 94% lignin, removal of lignin, but some percentage of lignin still it will be there. It cannot be removed, that your some 2%, 3%, 1%, 2% lignin, still it will be there. Percent crystallinity, I have checked that whatever I am showing the result here, this result is nothing but the basically your cellulose nanofiber. I am discussing here cellulose nanofiber percent crystallinity. If you see raw fiber, it's 58%. Cellulose nanofiber after chemical treatment 79%. Cellulose nanofiber is 72%, because if you do the reprocessing by virtue of ultrasonication, that reduction of the crystallinity will be generating. That's why cellulose fiber to cellulose nanofiber, little bit of reduction of the crystallinity has been noticed. And that method, Siegel method for calculating the cellulose crystallinity, we have used, that is called the peak height method, that is reported in the particular reference. The morphology analysis of the material, whatever we have developed by FESM and AFM analysis. This is the basically image of raw fiber, cellulose fiber after treatment, and cellulose nanofiber, and it is supernatant material. Okay, if you see cellulose fiber, that your whatever we are getting, it is really in nano dimension. Thickness is somewhere in 50 to 20 nanometer, and length is very, very high, few micrometer. Then exactly we have done with the basically morphological analysis and diameter calculation. Average diameter we have come up with at the 11.8 nanometer, and where standard deviation we have taken 4.7. Total number we have taken it's 221 by the image analysis process. And notwithstanding that, we have checked with the atomic force microscope by checking what is the basically thickness of this material. Thickness of the material, though it is coming little less, but whatever we are getting morphology from the FESM, that is reasonable. And here we are getting somewhere 4 to 5 nanometer, 4 to 5 nanometer of the thickness, average thickness, because here whatever we are drawing the line, based on the line, whatever it is touching, based on the thing, it is giving the thickness. That's why, but at least what I want to conclude here, that yes, we can compare the data, whatever we are getting the APSM with the AFM, and it is in the nanometer dimension. Means nanometer cellulose nanofiber we able to produce. Then we have checked the thermogravimetric analysis, thermal stability of the material. The definitely whenever removing of your lignin, all the things, then it will increase the thermal stability pure cellulose nanofiber. Okay, it is that's why thermal stability is getting increased a little bit. Okay, now that we are able to extract the cellulose nanofiber. Now cellulose nanofiber, which I want to utilize for the different application here. First, preparation of cellulose nanofiber based polymer composite. Here we want to utilize as a reinforcing material. Here, just for the checking of our basically thought process, whether this cellulose nanofiber can give a mechanical property improvement or not, we have taken a very normal polymer that is called the thermoplastic elastomer, that is called ACBS, polystyrene ethylene co-butylene styrene triblock copolymer CNF nanocomposite we have used. But processing of this material is very easy. That's why as a standard material we have used this block copolymer material. Okay, this any block copolymer, if you see, this is the structure of the block copolymer ACBS, where styrene moiety is there. This is the hard segment, and polymer rubber moiety, that is basically soft segment. Hard soft segment combination is there. That's why it is very easy to process as a thermoplastic. But application point of view, it will be acts as a rubber material. So as from the processing point of view, I thought that to check my concept, whether my material will enhance the mechanical property or not of the any polymer with the cellulose nanofiber, then I was trying to check it. That's why we have used for the material the solvent casting method to check our concept. But later on, we have done with that of the basically means a normal melt mixing method. And in melt mixing method, we are getting little bit of problem, but still we are getting very good enhancement of the property. Then this is the basically first we have dissolved the material, the THF, then we have add the cellulose nanofiber inside it, and this is the ACBS CNA film. This is the ACBS CNA film, and this is the basically different composition we have used. The pH at 0, 0.001, 0.005. Try to realize one thing. I am utilizing cellulose nanofiber. It's very, very less. You see, 0.001 pHr, 0.005 pHr. I am not going to the 1 pHr itself. With that of the pHr, with the 0.005 pHr, if it is giving the very good reinforcement, then we need not to add high amount of other reinforcing material. And here, another important factor, whatever I have not told you, that cellulose material is basically nothing but the polar in nature. There's a lot of OH group. Okay. Now, if it is only ACBS, there is no polarity in the ACBS. So if you add the one polar material to a non-polar material, then phase separation will be happening. Rather, agglomeration of the cellulose nanofiber, it will be happening in the matrix. As a result of it, what happened? We may not get the mechanical property improvement in the system. For the reason, what we have done, we have used malachinated grafted ACBS, where malachinated grafting has been done in the ACBS. So the polarity has been increased a little bit. As polarity is increasing in the system, so automatically interaction between cellulose fiber with that of the modified ACBS, that will be there, and definitely it's supposed to give the mechanical reinforcement property. Let's see how the interaction is going on. Basically, this is the FTR spectra of whatever. It's very difficult to see whether there is interaction with the cellulose fiber or not. But what we have done the basically succinate extraction of the composite material. If there is a interaction between the filler and the polymer, the residue, whatever it will be there, still that contain that particular part of the material. That's why after making the composite with 0.01%, 0.05% of the cellulose nanofiber with that of the polymers ACBS, we have done oxidation, and after oxidation we have checked whether there is a basically peak of the cellulose or not. And yes, you see this is the cellulose peak OH. There is a cellulose peak of the basically of 1628, and that's why we can conclude there is a interaction between the cellulose. There is an interaction between cellulose and the basically malic anhydride. That's why it has giving the mechanical reinforcement. This is the scheme. Whatever we have seen, we have shown. Then this is the interaction. This is the interaction. That's why it is inseparable. Inseparable. That's why if I compare this phenomena with that of the bound rubber, like any material, if we are using the any carbon black material, the carbon black will not able to separate out from the rubber if it is reinforced. Amount of reinforcing material, if it is high, bound rubber property will be very, very high. Here, similar type of things, as in the residue itself, there is a basically polymer, definite reinforcement has been happening like that way. So this is the way just we have proved there is a they are supposed to be interaction. After the seeing this interaction, definitely we have to check what is the mechanical property of our material. You have checked the mechanical property of our material. You see 0.0058% material is giving the manifold elements mechanical property than that of the normal ACBS square, normal ACBS square. Okay, almost 98% young modulus increment, 70% tensile strength increment has been reported. Then we have compared with the other material. ACBS with malic anhydride grafted with that of the basically this is material with we have used cipolite clay. When we have used the cipolite clay, 308% clay, it is giving that type of 105% young modulus 32 tensile increment of a tensile strength. If I compare with the cloisite 28 clay, it is giving the 408% clay, is giving 43% young modulus increment and 82% tensile increment. So if I compare that here cipolite clay and here cloisite 28 clay, whatever it is giving, that is somewhere 308%, here it is 408%, but our system, it is able to enhance the material property by 98% and 70%, only 0.00 PHR. Try to realize, that's why with minimum amount of material can give or enhance the mechanical property. This is the beauty. Then we have checked what is the basically morphological perception of this material. And if you use the basically higher amount of loading, we have seen there is agglomeration, and you see malic anhydride grafted ACBS with 0.005 PHR, it is giving very good basically morphology. You see uniform morphology it is giving, so mechanical property improvement will be there. And yes, after the stretching of 0.001 and 0.0058% of addition of the CNA, then fiber formation has been happening, and is showing that alignment of the material of the cellulose fiber, and that's why it is giving the basically mechanical property improvement. Where you see as there is increment of the cellulose fiber content, then agglomeration is happening and it is breaking the basically cellulose fiber. It's very fast that it is not able to align whatever you used to get with 0.005 or 0.001% of cellulose present percentage. So what I want to conclude here, mechanical property will increase with minimum amount of addition of the cellulose fiber. This is unpublished paper where we have used the polyurethane as a matrix, and we have added the cellulose nanofiber. Here again, if you see, this is the 0.03% of cellulose nanofiber. It is giving the highest mechanical property than that of your knit cellulose knit polyurethane material. So means if you want to utilize this material as a reinforcing material, yes, it can be utilized. And near future, if we are able to make a composite instead of the carbon fiber composite where structured composite has been used, then yes, that can be replaced, and people are working on it. I think near future, instead of utilizing the carbon nanofiber or carbon nanodium, we can utilize the carbon cellulose nanofiber instead of that particular material. And here 300% young modulus increment and 200% tensile strength increment has been has been observed. It has been not published till now. Just we are working on it. Now, this is one aspect, that is the reinforcement property of the material can be shown. Next, I am going to the basically, so this cellulose nanofiber can be utilized for the biomedical application also. Here, we are utilizing this material with that of the, we are make a composite with that of the bio extract from the, and we have added the sodium alginate as a basically matrix material also, and we are making a bio sponge for the different application, for the wound dressing application itself. Let's see what is the composition here. This is the composition I am saying here. Sodium alginate we have used, cellulose nanofiber we have used, and you see double distilled water. This is the basically double distilled water, cellulose alginate. Okay, SA alginate, double distilled DW, and your GE, gilai water, and your CNM cellulose nanofiber. This is the composition, and RWGE SA CNA means cellulose nanofiber impregnated in basically alginate, added with the gilai extract, added with the rice water. If you see why I am interested to utilize this gilai water and rice water, gilai water has a medicinal value. Okay, if you can recall, earlier time and till date also, the old people they used to use, if your stomach is upset, they used to take a glass of gilai extract. It will be okay. Rice water also, when you're something you are not feeling good, then for easy digestion and antibacterial properties there with the rice water also. That's why people used to use the rice water when it is required and when you are getting upset with your stomach. So with that other things, then we can utilize this material to make an antimicrobial material to utilize the wound dressing application. Let's see. This is the microstructure characterization of the different type of material. This is the DW alginate, means distilled water and only alginate, and gilai water only alginate. And here this is the rice water, gilai water, sodium alginate, and CNF. You see the structure, that uniformity of the structure is almost in the different magnification. You see it's very good structure it has generated. It has very good structure it has generated. And this structure is very important, and because if there is a good structure or morphological structure, dimensional stability will be very good. Dimensional stability will be very good. And here we are most interested with the rice water, alginate, and CNA because it may give the better property because it is honeycomb structure, honeycomb-like structure. And that is called basically why it is coming the honeycomb-like structure, because here calcium ion that can act as chelating type of things, and as a result of it will come too close to each other in different direction. That's where honeycomb structure it will be generating. So then we have checked the compression properties. Compression properties almost 8 times higher young modulus, 4 times higher tensile modulus with that of the simple alginate itself. Now, if we add basically your sodium alginate nanofiber, or without the basically other materials of cellulose, without the basically your rice water, then it will come up with a 6 times higher modulus, means 2 times higher tensile strength. So what I want to tell you that whatever I have told you, it's supposed to be a good mechanical property and compressive strength. Yes, if you see that mechanical property of this combination is very good. Now with that of the good mechanical property material, we want to check whether it has an antimicrobial property or not. Here, E. coli and 2 different type of bacteria we have used, and you see that your bacteria culture process, we have seen that the combination of the rice water, gilai water, sodium alginate, it is giving very good antibacterial property. It's giving the very good antibacterial property than the combination of the other like sodium alginate, rice water, and CNF, gilai water, sodium alginate, and CNF. That's why the combination of rice water, gilai water, sodium alginate, and with CNF, which is giving the mechanical property stability, then it is giving the very good stability in the system. Now, this is the quantitative value. This is the quantitative value that is showing the good antibacterial property. Now, properties of an ideal wound dressing material, it's supposed to be some antibacterial property that already I have shown to you. Okay, it's supposed to easy to apply and comfortable to wear. That yes, it can be utilized. Non-adherent. It's supposed to cost effective because we are using the waste material. then yes, it's supposed to be cost effective also. Minimum dressing changes, and with once you have put it, it's supposed not to be changed. Mechanical stability is very important. Provide barrier to external contaminants, non-toxicity and biocompatibility. And most important thing is that in the moist environment, it's supposed to be a little bit stabilized. Otherwise, in the moist environment, if it is not stable, then it will, what happen? It will basically swell. If it is swell, that wound dressing applications for the long duration of 2 months, 3 months time, or 1 month's time, it cannot be done. So that porosity is also important. Porosity, so that your skin can propagate or skin can generate with that other porosity. Okay. So automatically till now, if you see our material, whatever we have developed, that is rice water, gilai water, sodium alginate, and CNA composite. After 5 hours time, it is not stable in the water media. Means till now, whatever we have developed, that cannot be utilized in the basically wound dressing application, because it is not stable. So some modification is still needed to make it stabilize. So what we can do? Definitely we can do. Here we have reported that biopolyurethane coating sodium alginate CNF sponge we can utilize, where your mechanical stability in the wet environment can be retained, and so that for the long duration of time it is not required to change. And here we have done the same thing. We have developed the castor oil based or linseed oil based biopolyurethane coating, biopolyurethane material that has been coated with that of the cellulose sponge, and that cellulose sponge has been used for the basically wound dressing application. This is the basically your reaction mechanism to making the basically epoxidation of the cellulose, epoxidation of your epoxidized linseed oil and the castor oil. After the epoxidation, we used to add the basically NCO, IPDI, and as a result of it, we are getting the basically NCO terminated polyurethane material. This NCO terminated polyurethane material can be utilized for as a coating. And here, whatever OH NCO group is, the very minimum OH group is there. This OH NCO group is there. This NCO group is very useful for us to make a coating, because this will react with the OH surface OH group of the basically cellulose nanofiber. As a result of it, it will giving a small but thin like coating with that of the mechanical stability, with the mechanical covalently bonded with the cellulose plus polyurethane. This is the epoxidation, epoxidation oil. This is the basically proof that after the epoxidation, there is no double bond in the FTR also, and your NMR also, that has been proven. And here, this is the castor oil fatty acid. And here, basically, again, that is the characteristic of castor oil fatty acid. This is the basically characteristics peak. Okay, and this is the basically reaction of mixing of the two material. After the mixing, then epoxidation, and the ratio whatever we have used, that is the 0.08. Basically, it is NCO is to OH ratio, whatever we have seen. Then if we able to do it, then used to give the basically good mechanical property of the material. Okay, this is the chemistry. I'm not interested with that thing now. Okay, that whatever biopolyurethane we have able to generate, that we able to generate a NCO terminated polyurethane, that little amount of OH NCO group still it is there, and that is useful to do the reaction with the cellulose material. The OH, whatever it is present, it will react with that of the your NCO, with that of the OH group. So this is the coating, and this is the final coating of the material. Now see what happened. This is the different dilution we have checked. What dilution it will be giving the very good result. If you use the maximum amount of biopolyurethane to do the coating, then definitely it will not give you the good property, because porosity, whatever it is there, it will block. That's why minimum, basically maximum dilution you have to do, so that you will be getting the good property. With thin layer of coating, it will be giving. After the coating, basically microstructure of the material, just we have checked microstructure of the material, that is giving the very good. This is the basically D, and here if you see 80% dilution, that is giving the very good result. And the 80% dilution of the prepared cellulose PU, that is giving the better result, and we have used for the further analysis here. Mechanical property, it has increased compressive strength and compression modulus, both the things it has increased. And but for the our purpose, we have utilized this material for the further application. Okay, cyclic stability, cyclic strength, that is also increased manifold. Whatever we used to get a very minimum compressive strength, now you are getting the high compressive strength. You must appreciate me, because you are using polyurethane as a coating material. Polyurethane as a coating material, mechanical property definitely will increase. Polyurethane, because it is in the rubbery grade, whatever you have developed, the automatic compression, cyclic compressive strength also it will increase manifold. Now, if you see what happened during in the moist environment itself, in the moist environment, whatever it was not able to stand for the 5 hours of time, now you see after 24 hours of time, our material still it is in the exact condition. And it is flexible, and this is the basically visual structure. Whatever I have shown to you, it can be folded, it can be reutilized. That's why this material, and it is very porous in nature. Now this material is very useful for us to utilize the different application for the wound dressing application. Highly stable, porous, and flexible, that is really required for the wound dressing application. And we have checked the biocompatibility and cell viability of the material. Then we have used the human keratinide cell, and it is really non-toxic in material. It is really compatible with the cell, and hematotoxicity and hemostatic performance you have checked. There is no repulsive interaction with the blood. It is really compatible with the blood. Means whatever we require for the biomedical application, that has been proven. And we have checked acute dermal irritation corrosion test with that other mice model. And after the 72 hours, we have seen there is no irritation after thin layer coating of our material. And notwithstanding that, we have checked the histopathology of the excised skin section, and we have seen there is no change in the there is no generation of tumor cell in the basically mice, whatever we have quoted. So whatever I want to conclude from here, that our material is really good to utilize for the biomedical application, and definitely we are working in it, and hopefully we can make it it's a very good stabilized property, whatever it is available then in the market itself. Now I'm coming to the next part of my presentation, that whatever biomedical application, mechanical reinforcement I have shown. Now, why not to utilize this material for the basically a high thermal insulation material? But for this thermal insulation material, we have developed three-dimensional porous material that will give us that particular property. Here, we have developed an aerogel type of material, or aerogel material. You must be knowing aerogel is a mesoporous solid formed by replacement of the solid in a gel with gas. The term aerogel does not refer to a particular substrate, but rather to a geometry. Here, this is the process we used to use for the getting the cellulose of the aerogel. First, it is the gel, means that is the polymer plus the water. Just we have done the gelation, then it is reductional freeze. If you do, then after the reductional freezing, we have to do the sublimation. Directly sublimation, that we have that instrument, that is your lyophilizer machine instrument is there. You reduce the pressure, you reduce the temperature, then it will be going directly from the sublimation from the basically solid to a vapor. That's why the morphology of the material, whatever it was inside, that will be remain intact. Our research interest is that material, whatever we will be using, that is a cellulose, and that means a three-dimensional porous structure will be generating. Cellulose aerogel will be developing, and we can add the silica, graphene, or some resorcinol formaldehyde resin or pectin type of material. But here I will not be using too much of things. I will be checking the aerogel first, whether it is giving the thermal insulating property or not, or to further increment the thermal insulating property, or to increase the fragile characteristics of the material, we can do some modification of material. Let's see what is going on and why this is important. In building envelope, but if we able to make that type of material, that will give you the coating, thermal property, thermal insulating property, if it is very, very high, then during summer and during winter, both the time, we can save a lot of energy. And in the cryogenic insulation also, in the high temperature also, if we able to make a aerogel type of things or aerogel, then it can give the very good application with low cost. Okay, and you must have seen that silica aerogel has been used for the liquid tank, helium liquid tank, or your nitrogen liquid nitrogen tank. And here there basically specific gravity of the silica is very, very high, thermal insulation is very, very less also, but I want to replace that type of material, high specific gravity material, with another cellulose material. This is the research objective, that to maximize the utilization of the bioresources. Then definitely I'm thinking to reduce the cost and durability of the existing aerogel, preparation of cellulose nanofiber based aerogel, and its various characterization also I will be showing here. First, preparation of aerogel, definitely whatever supernatant material I have shown to you here. If we make a basically first hydrogel, if I make a hydrogel type of material first, then this different type of concentration of cellulose of the material we have used without water, we have seen the rheological property. To check the rheological property, which material is giving the good rheological property. Based on the rheological property, generally we can predetermine which concentration it will be giving the better result. As per our knowledge, 1 weight percent or 0.7 weight percent or 1.27 weight percent, 1.25 weight percent, that is giving the good rheological property. And that's why that 1.28 percent, that is the your density to porosity, it is giving the better result. And that's why this combination is useful for us. And this is the stable, whatever I'm showing, there is different composition, theoretical density, porosity, linear, all the things. And if you see porosity, we are getting 99.02%. And if you decrease the thing, porosity will increase, but property wise it's supposed to match. That's why whatever 1.25 or 1.00, then we can utilize for our further application. This is the drying technique. I have told you also that the freeze drying process that has been used, that we used to go for the physical freezing first, then we used to evaporate our material, water from the system, then it will remain intact. And this is the prepared material. It is so light that it can stay in a marigold flower. You see, this is our material, and it is so strong that it is almost 500 grams of weight. It can withstand that type of weight, and it is flexible that it can be basically fold, and it can put in a glass. Okay, you see, density is 8 to 20 kg per meter cube, and porosity is 99.5 to 98.6% you are getting. So, and aerogel, we have checked whether there is any defect or not. That is the CT scan image. It is showing there is no basically deformation inside the material. This is the X-ray microtomic CT scan image of our material, three-dimensional image material. You see there is really cellulose fiber. It is uniformly distributed. And what I want to mean it here, there is a lot of air inside the material. So definitely that air, whatever its thermal conductivity is there, it will be almost near to air. Air thermal conductivity is 25 milliwatt per meter Kelvin. Please listen. Air thermal conductivity is 25 milliwatt per meter Kelvin. And we have to getting that particular thermal conductivity with that other range of air, then our we will be getting the success. This is the property of aerogel, but for getting a aerogel, it's supposed to be basically mesoporous range. We have checked whether it is a mesoporous or not. Yes, almost somewhere in, you see 82% of the basically pore size, or 72%, 74% of pore size, it is in the mesoporous range. As it is in mesoporous range means it is pore diameter is 4 to 50 nanometer. Okay, now if you see that your mean free path of air, it is 68 to 70 nanometer. Now for propagating your thermal energy with that of the mean free path, where air is somewhere in 68 to 70, it is not getting, because mean free path, it is restricted because it is within 50 nanometer. As it is 50 nanometer range, it is not getting the thermal energy to propagate. Rather, it will reflect again and again. It will reflect again and again, and all this is the reflected. And to maintain the thermal your basically mean free path, that's why thermal stability, thermal conductivity will reduce manifold. This is the basically reason. That's why we supposed to get a thermal stability or thermal basically transport property. It's very, very less. This is a mechanical property I have shown you, and here 1.7% by cellulose content is giving better result, but I am interested with the 1.2 and 1.5 or 1%. Okay. To see cyclic stability, you have checked cyclic stability also, it is giving very good result as per the requirement. And you see this is the thermal conductivity of the aerogel. Only aerogel of cellulose, you see we have reached up to 25.50 with 1 weight% present of the cellulose fiber in the water. After freeze drying, this water is removed, and it is giving 25 0.5 milliwatt per meter Kelvin. And whatever we know thermal conductivity of air is 25 milliwatt per meter Kelvin. So we have reached to a certain level. This is our work, CNF aerosol. This is the related literature. Silica aerosol, it is little less than that, whatever you have reported. This is the air, polyurethane foam people have used, glass wool, magnesia, and mineral wools people have shown. But now our target to reduce further that thermal conductivity of aerosol so that we can utilize this material in the different applications. There are the application area we can think about: energy efficiency building, cryogenic insulation, high temperature insulation, body jacket. Yes, we can utilize. Okay, this is the phenomenon of what I told you also. This is the mechanism, because you see mean free path of air, it is 70 nanometer. Mean free path, whatever, it is not able to maintain the mean free path inside the material. So automatically the conduction, conductance, and the different type of conduction, convection, and radiation, the total things that is to reduce. And as a result of it, you will be getting many reduction of the thermal conductivity, huge reduction of the thermal conductivity value. So then what I told you, till now we have reached up to 25.5. Now we want to modify our material. This is the pulping, then cellulose nanofiber aerosol. Then we are making this is the hydrogel. After the hydrogel, we have done basically some layered by layered assembly. After the layered by layered assembly, by adding a PMSQ, basically it is silicon polymer, and we have CIPET as a clay to making it basically a less flammability. And after adding the PMSQ, it is in decreasing the further. Basically PMSQ, it is a silica precursor, and whatever I have shown to you, that is the basically silica thermal conductivity is very silica aerosol thermal conductivity is a little less. That's why you are targeting to combine this material to reduce the thermal conductivity again. And we have done the freeze drying method, -40, -80, and liquid nitrogen itself. Then we have seen, then this is the lyophilized product, and we have checked. We have then, after the lyophilization, we have done some polyurethane polylactic acid coated in the system in the aerosol by spray coating, and we have checked what is the thermal conductivity. This is the structural analysis I have shown you. After the coating of the basically your PLA, that your contact angle is decreasing manifold, and it is come up with a 139 degree like that way. And that's why this is used 113 to 114 like that way. So thermal conductivity, whatever I have told you, that comparing to the other material and reported value, that this is our work I have told you. Now we have reached to the product where 18.28 milliwatt per meter Kelvin we have able to reach it. You try to see this CNF, PMSQ, CIPET aerosol, we have reached up to 18.28 milliwatt per meter Kelvin. It's a huge reduction. It is less than that of the your silica aerosol people have reported. So there is a lot of scope. Already we have filed a patent of this particular work, and I am hopeful that we can do the commercialization of this particular product also. So this is the comparison. This is our work, basically current work. This is the current work I am showing. Then that is the comparison of the other material that is shown the particular things. Most important thing is that our material is basically bio-origin, number one. Number two, basically very easy to do the processing. And finally, thermal conductivity is less, and it is not biohazard. But another important thing is that our material till now, if we want to utilize in the building insulation material, then flammability is supposed to be very less. Then that's why what I told you, I have added the CIPET clay to reduce the flammability, and we have checked the different type of horizontal flame test, and you see when we have used the basically that combination of CIPET and PMSQ, then you see this is that burning is not propagating whatever it was propagating for this particular one, and burning is not propagating here whatever it was propagating with that of the without material, without basically other material. Here the digital image of the obtained the vertical burning test. Here it was totally char formation is there, but here you see at least it is burned, black formation is happening, but it is not totally burned. Its char formation is not happening like that way. So what I want to tell you here, that there is a lot of scope to do the research in this particular direction, how to increase the flammability, how to decrease the flammability, all the things we are working on it. And I think we are hopeful we can produce much better products, whatever we are doing today now. There are different type of potential application of the aerogel. Okay, ultra lightweight, different type of space shuttle, propellant or propellant tank. We can think. Definitely sandwich structure we can develop, and later on we are working on to make a development of the cryogenic insulation tank. We are in the process to develop that type of material with the cellulose as a material. Flexible aerogel blanket, its installation I have seen. This is the aerogel based material. This is the cellulose based aerogel people are using, and thermal conductivity is only simple aerogel based cellulose based aerogel. Now just I'm going to quickly to the super hydrophobic cellulose aerogel for oil water separation. The cellulose, whatever I have shown to you, now cellulose you must be knowing it has a basically OH group and it is hydrophilic in nature. Now I want to develop a material with that of the cellulose material that can be totally hydrophobic in nature. Here we have utilized one type of modification, actually sterile acid chloride modification of cellulose nanofiber without addition of fluorine compound to make it super hydrophobic. Then as it is super hydrophobic in nature, then it can be utilized as a oil water separation. Let's see, we have used the CNF. Here I have mentioned is the NFC, but it is CNF, and we have added some 5% PVA to make its dimensional stability, okay, and low density also, porosity also 99.1% aerogel we have made. And this is basically morphology, interconnected porous structure for the oil absorption capacity. And we have done the basically some modification, sterile acid chloride modification, what I told you in the surface of the OH group. And this surface of the OH group now converted to the basically aliphatic chain type of things, aliphatic and hydrocarbon type of things. That's why it is super hydrophobic in nature. Then I'll show you, this is the FTIR, because I'm running when the time. I don't want to go in details of the chemistry part. I'm showing the basically technology part. You see, comparative study of the modification of unmodified aerogel. You see the contact angle of the water of unmodified material. It is immediately absorb the oil and water at a time. This is the unmodified material. Now, if you do the modification, you see oil drop, it is absorbed by the material. And this is the water droplet that we have added some basically colorant, blue color we have added so that it can be visible. And you see it is not able to absorb. And the material, whatever we are using to the water media, it is not able to get disintegrated. Means our material is water repellent, but it is oleophilic in nature. It can absorb the oil. So see, this is the basically compressive strength. Means if you use the NFC, PVA, and sterile acid chloride material modified, mechanical properties increasing. And here, this is the basically oil spill. Just I'm showing you the. Just 1 second. I'm showing you the video basically. I'm showing you the video. You can see. You can see from the video one, it is not touching the water, and here oil absorbs on unmodified aerogel. It is absorbing the water and oil at a time. But here you see this is a basically aerogel, modified aerogel, and it is specifically absorbing the basically oil from the oil water. So we have done the basically absorption capacity and all the details we have seen. But chloroform is the material that has been basically absorbed highly with our material, whatever we have developed. There is a 105 gram per gram of NFC. And this is the basically reusability study we have done. Means after one time use, whether it can be utilized for the n number of time or not. Mechanical squeezing, then we have checked. You see, after mechanical squeezing, cyclic basically means reusability you have checked. We have seen that modified material red one, it's still after 15 cycle some 16%, 60% oil absorption capacity still it is there. capacity of the material still 60% still it is there after 15%, 15 times recycling also. So our material is robust. Our material can be utilized for the oil water separation. Most important thing is that the take home message in this particular work is that whatever it was hydrophilic in nature, we make it hydrophobic, and this hydrophobic material can be utilized for the oil water separation, and it has a very good market because oil water separation is a really important issue nowadays throughout the basically globe, and where there is a chemical contamination of the water with that of the industry, that is also our material can be utilized. So addition of PBA, that reusability is increasing. Which other potential application, I have just this is the basically aircraft structure, car component, solar panel, large plastic furniture, important battery supercapacitor, with cosmetic application, whatever I have not shown, though I am working a little bit in this direction also, but there is a lot of certain time I cannot tell all the things, but yes, there is a lot many applications also. CNM multi-layer flame, I have told, I have not shown my work here. Means already we have developed that type of material. Okay, water stable membrane through the chemical modification. Okay, CNF filament or yarn. Okay, CNF rheology and stability modifier that can also be utilized or people are using. Okay, 3D printing porous material can also be utilized. Bacterial nanocellulose as a biocompatible high porous scaffold, already biomacromolecule it has been reported. These are the few publications, whatever my work has been published in the different article from this work, whatever I have discussed. I would like to acknowledge my student support in my research group and financial support from IIT Roorkee, ACRB Government of India, DST Government of India, Ministry of Education, MIF Foundation, Japan. Thank you for your kind attention. Any question, please? Any question? Please.
Your participants? Yes, please. If you are having any queries, then you can ask. Dr. Maji is here.
Sir, I have a question in the dewaxing step in the raw mango.
Please.
Sir, you have used 2:1 benzene ethanol. Benzene is banned actually. So
that's why nowadays instead of benzene, basically we are using basically your xylene we are using nowadays.
Okay? Yeah. Xylene is safer solvent.
Actually, though, but this is the last some few years back I have developed the process, but we have changed the process nowadays. Okay, that same comment. Thank you very much. Already same comment I have received from the reviewer also.
Okay. So this industrial production of this have you done, sir, or is it still in the laboratory stage?
Actually, industrial production, basically CIPET Mumbai, they are doing. Actually, okay. in our lab already we have done little bit of scale up. Already we have achieved at least 100 gram per day. 100 gram per day in a lab, it is also huge. And if you want to, if you purchase the cellulose nanofiber commercially available, you cannot imagine the cost. Cost is somewhere in 10 gram of material in the dispersed in the water media. It is almost some 30,000 per 10 gram.
Yes. Even Sigma Aldrich also sells.
Very good. That's why I want to basically mention beginning of my talk that it is upcycling. It is not recycling. It is not downcycling. Basically, it is recycling. Specifically, it is upcycling. Value addition of the material we are getting.
Okay. Thank you, sir.
Thank you very much. It's a nice question.
Sir, for this aerosols, you have told about some squeezing test, mechanical squeezing test.
Yes.
For cycles. Sir, how that was carried out?
Basically, mechanical is very simple. Basically, after the putting in the oil water mixer, then our material will absorb the only oil. Now you squeeze it, then oil will remove. Then it is sponge type of things.
Sir, that is done manually, like
that is basically we make a one setup so that if you're putting inside,
it will rotate.
It will rotate like that. Okay, then it will remove. Then notwithstanding that, what we used to do after squeezing, we used to wash it in the basically hexane.
Yes.
If
Yes.
you wash it is hexane, then
Hmm.
residual oil, whatever it is there, it will totally remove.
Okay. So this is not like any standard method. This is like a lab setup you have
Yes.
made for mechanical setup, basically, where two rotating plates or rotating discs would be there, and inside this you are keeping this aerogel foam. Aerogel is basically
Yes.
foam.
Yes. Foam-like structure. Yes.
Foam like structure. Okay, sir. Thank you, sir.
Hmm.
Any other clarifications? Participants, if you are having any doubts and you need some clarifications, then you can ask. Dr. Pradip sir is here.
Any
Because
question you please, if you think just this is one good topic to do the research. There are a lot of opportunities.
Yes, sir.
There's
This
a lot
is very
of opportunity in this particular.
opportunities are there. Yes, sir.
Hmm.
A new area we can say cellulose
Yes.
nanofibers and lignocellulosic material
Yes.
extraction and application, particularly application.
Application is most important nowadays.
Most important, and what I saw in your presentation, you have shown a very like wider range of application which many people are like not able to. Extraction is a bit explored area, but properly putting into some application is like very attractive, and you presented it quite well mannered. Thank you, sir. Any part?
Thank you, ma'am.
Yeah, yes, sir. Participants, if you are having any, if you need any clarification, then yes, Dr. Maji is here because we won't get such opportunities all the time. Now he is here, he can explain you or he can clarify your doubts. Anyone is working on polyurethane or aerogels or zerogels or extraction of carbon nanofibers, then it will be really a like relevant topic for all. I don't think any further questions are there. Okay, then if you are having like in because we have this session is recorded throughout, then after if you need further clarification, then you can contact us or we can send your query to sir, or you can contact him directly also because
Yes. My phone number and email ID is available in the institute website. Okay, you please go through it and you will be getting all the details. Okay.
Yes, you can contact him anytime, no problem. Okay. Thank you, Dr. Pradip sir, for giving such a wonderful presentation and particularly highlighting the application areas of lignocellulosic carbon fiber, basically the cellulose carbon nanofibers, and highlighting the various methods available to extract those carbon nanofibers as well as their application areas. Thank you, sir. Thank you. This total session was thoroughly knowledge based, and I hope and I am pretty sure our participants have benefited a lot from your discussion, and the way of your presentation was spectacular. We have thoroughly enjoyed your session. Thank you, sir. Thank you for giving your time and and accepting our invitation to attend our participants for this FDP session. Thank you, sir.
Okay, thank you, ma'am. Just I'm leaving now.
Yes, sir. Yes.
Okay, thank you.
Thank you, sir. Dear participants, this was the last session for today. So if you are having any doubt related to Professor Maji's talk, then you can directly contact him or you can ask your queries to us. There is no such hesitation on that, and we are ready to clarify all these things. And related to this FDP program, if you are having or facing any kind of difficulty, then feel free to mail us regarding your attendance and other thing. During each session, I am sharing the link or basically a Google form with you all. During that time, try to fill your attendance, try to mark your attendance, because for each session there is this attendance is mandatory. And PPT I'll be sharing. I think at the end of our 5-day program, I'll be clubbing all these sessions materials, and what our first speaker, Mr. Amit Shah, also given some information, some link about recycling processes, like some YouTube links were provided during our first morning session. So all these things I'll be clubbing and I'll be sharing with you all at a time. So thank you all. Thank you for attending the FDP and being so patient. Tomorrow we'll start again from 10 a.m. Thank you all. Good
Thank
afternoon.
you, ma'am. Thank you, ma'am.